Good day. This lesson is all about Green's theorem. It is considered a remarkable and beautiful theorem that expresses a double integral over a plane region in terms of a line integral around its boundary. Here is the objective of this lesson. At the end of the lesson, you're expected to demonstrate a double integral over a plane region in terms of a line integral around its boundary. This is the overview of Green's theorem. It gives us a relationship between the line integral of a two-dimensional vector field over a closed path in the plane and a double integral over the region it encloses. The fact that the integral of a two-dimensional conservative field over a closed path is zero is a special case of Green's theorem. Then we have the theorem about Green's theorem. Let R be simply connected plane region whose boundary is a simple, closed, piecewise smooth curve C oriented counterclockwise. If f of xy and g of xy are continuous and have continuous first partial derivatives on some open set containing R, then the integral of f of xy dx plus g of xy dy along the curve C is equal to the double integral of the partial derivative of g with respect to x minus the partial derivative of f with respect to y times differential a along the region R. It is common practice to denote a line integral around a simple closed curve by an integral sign with a superimposed circle, as can be seen from this notation. So that with this notation, we have now the previous formula from the previous slide will be written as we have the integral of f of xy dx plus g of xy dy with the integral sign being a superimposed circle along the curve C is equal to the integral of f of xy dx plus g of xy dy along the curve C is equal to the double integral of the quantity of partial g with respect to x minus partial f with respect to y times the differential a along the region R. Let us have this example. Example 1, it says here, evaluate the integral of x dx minus, we have it as x squared y squared dy, where C is a triangle with vertices 0, 0, 0, 1, 1, 1, positively oriented. So we have here now the region drawn, and we have this region drawn by using the three coordinates, which are we have 0, 0, 1, 1, and 0, 1. It forms here a triangle. So if we're going to evaluate now the given integral, so we can now have it as we have the double integral of you have x dx minus x squared y squared or x squared y squared dy. Then we have along the curve C. So this is equivalent to what we have in the said notation here. So with that, we can write now the formula to be the double integral of the partial derivative of the function g with respect to x minus partial derivative of the function f with respect to y times the differential a along the region R now. So with that, let us get the partial derivative of your function g with respect to x first. So your partial, or rather your function g here is, we have it as x squared y squared. And if you're going to get the partial derivative of your function g with respect to x, so in this case, y will now be considered as constant. So copy y squared, and then the derivative of x squared is 2x. So this is now 2x y squared. Then let us also get the function f. And the function f is equal to x. And with that, when we are to get the partial derivative of this function, f with respect to y, since x is considered as constant, so the derivative of this function f with respect to y is 0. And then we're going to find also now the limits for your region. So before we substitute this function, partial derivatives rather, of f with respect to y and partial g with respect to x. So in this case, you need to find first your dA. So your dA can be expressed as dx dy, as we have learned last time in your Math 146 or rather Math 147, or this can also be written as dy dx. So if I will use a vertical strip here, I would have dA to be dy dx. If I will use a horizontal strip, I will have dx dy as my dA. So if I will now use this vertical strip, again, I will use dy dx. So I will use this one. So that we have here now, the partial derivative of your g with respect to x is equal to 2xy squared. Then the partial derivative of your function f with respect to y is 0. Then as I mentioned, I will use dy dx for my dA. What about now the limits? The limits can be found by, you have here your dy as the inner variable of integration, so that the inner limit will now be just simply your function y here. So it's y up, and we have it as y down. Then for your dx, it will be abscissa right and abscissa left. So let us get the abscissa right and abscissa left, the outer limit first. So the outer limit can be found from the boundary of the region, which we have it as x equals 0 and x equals 1. And for the limits of your differential y, we have it as y up and y down. So what is your y up? Y up obviously is equal to 1. What about your y down? So we can get our corresponding y here by getting the equation of this line. So what will be the equation of this line? So as we have last time learned that in equation of a line, we use the formula y minus y1 equals m times the quantity x minus x1. And that the m here, or slope, is rise over run, or simply you have it as, so we have here now y2 minus y1 all over x2 minus x1. So let us consider the first point here at 0, 0 as x1, y1, and then the point here 1, 1 is our x2, y2. So using this formula now, rather, we have it as 1 minus 0 is 1. Then we have also in the denominator, 1 minus 0 is 1. So this slope is equal to 1. So with that, we will now use the equation here. We have it as y minus, let us use again x1, y1 here. This is now 0 equals m is 1 times x minus 0. So therefore, y equals x. So our y down here is just simply the equation of your line, y equals x. So let us just simply have it as x. Then we have now the quantity 2x y squared times the differential dy dx. So integrating now, we perform the innermost part first. So the integral of 2xy squared dy. So we will copy the constant 2x, then get the derivative of your y squared to be y cubed all over 3. Then the limits is from x to 1. Then we write here dx. Then also we copy the limits of your outer integral, which is 0, 1. So then we now isolate the constant. So this is now 2x, or rather 2 over 3x. Then we're going to apply now. We have it as the limits here to be 1 and x. So the upper limit first, so that is 1 cubed minus quantity x cubed. Then we write here dx. Then the limits is from 0 to 1. Then with that, we now have to integrate, or rather to simplify. By the way, this should be 2/3. So simplifying it, we have it now as we have the limits from 0 to 1. Then this is now 2x over 3 times the quantity 1 minus x cubed dx. So with that, we now have to multiply 2x over 3 to your binomial. So we have here now as 2x over 3 minus 2x to the 4th over 3. Then let us now integrate. We have here now the integral of 2x over 3 dx is 2x squared over 2 times 3 is 6. While here we have it as 2x to the 5th over 5 times 3 is 15 from 0 to 1. So simplifying this will be 1/3. And that is we have x squared minus 2x to the 5th over 15 from 0 to 1. So applying now the limits, we have here as 1/3 times quantity 1 squared is still 1 minus 2 over 15. Then you have 1 to the 5th, this is still 1. Then we have the limit 0. So if I'm going to substitute here, that will be 0. Also here 0. So with that, this is just now 0. So simplifying it, we have it now as 1/3 minus 2 over 15. And that when we simplify this, let me just write it here. So this is now equal to LCD is 15. Then you have here now as 15 divided by 3 is 5 times 1 is 5. So this is obtaining the numerator part. While here, we have it as 2. So therefore, we have it now as equal to 3 over 15. And we can simplify this further as 1 over 5. By the way, I forgot to include the negative sign for x squared, y squared. So let me just include that. So we write here now as negative x squared, y squared. So we have it as, when you get a derivative, it is, or rather the partial derivative, it is negative 2xy squared. So all of this should have the negative sign. And so I'll just place here a negative sign, a negative sign, a negative sign. Then you have here a negative sign. So then I have here a negative sign. So therefore, the answer is negative 1 over 5. So this is how we solve problem number 1.